used in order to change the directing power of nitro, which is meta, into the orthopara. So to remind you of how this works, we start with benzene. Nitration gives you nitrobenzene, and I'm just for the fun of it, nitrate again. That gives you dinitrobenzene. Notice this can be done completely selectively because the product of this reaction, nitrobenzene, is much less reactive than the benzene starting material, and the product of this reaction, dinitrobenzene, is again much less reactive, much less electron-rich than nitrobenzene itself. Okay? So you stop at each stage of the sequence without any over-nitration. Just doesn't happen. And so then we can reduce this, and the way we did this was also catalytic hydrogenation. And the popular catalyst that we used there was nickel. And that reduced the nitro group to the amine. So this is one way of making benzene amines. And it's a way of making only benzene amines that have two hydrogens on them. In other words, primary benzene amines. If you want to introduce substituents here, you have to, at this stage, stage 3, use alkylation chemistry. But we'll learn a way to, with its problems of over-alkylation. But we'll learn a way in a minute of getting around that too. Remember also that in the orthopara versus meta directing game, we can reverse this reduction by a different reagent, namely oxidation with a per-oxycarboxylic acid, typically trifluoro-per-acetic acid, although other per-acetic acids will work. So here is a solution to the over-alkylation problem, although it is, in this case, also limited to making primary amines. So, and therefore avoid the over-alkylation of, say, ammonia to stop at the primary amine stage. And for that, we use a masked ammonia equivalent. And it's embedded in this beast here, which is 1,2-benzene dicarboximide. We didn't learn that, and we won't test for that. Common name is phthalimide. It's basically derived from benzene dicarboxylic acid. And we talked a little bit about making the anhydride. But if you treat this guy with ammonia, and the industrial prep calls ammonia at 300 degrees, it's a bad reaction, but it works in the end. It's a bad with respect to stringent conditions, but it works like a charm, 97%. You get what essentially amounts to a bis amide. So the reason that you need 300 degrees, if you recall, making amides from the carboxylic acid and an amine was bad because the first thing that will happen is you get the ammonium carboxylate. Okay? The acid protonates the amine, and that drops the energy. This is very exothermic. You drop down in energy, and you have to come back out of this hole to generate the carboxylic acid, in this case dicarboxylic acid, and ammonia, again free. And so for that, you need 300 degrees. So then, every now and then, the ammonia will attack at the carbonyl function, the carboxy function, addition elimination. Okay? So that's the mechanism of making carboxylic amides from carboxylic acid. It adds, the electron pair comes back, the OH is turned into H2O, the leaving group, it takes off. So you make a monoamide, and the NH2 of the monoamide then attacks again. Now, intramolecularly, that's a little better overall, by addition elimination, and that gives you this so-called IMI. Okay? And I won't test for that, but it's just the way it goes topologically. So it's a bis amide of this dicarboxylic acid. The essence, and you can buy this. So the essence of this stuff is that this proton is acidic. Much more acidic than a normal amide proton to make the amidates. Remember that acidity was a little over 20, specifically 22, but let's call it 20. Here, this drops down to about 8. So this is more acidic than an alcohol, more acidic than water. Consequently, you can deprotonate just with carbonate, soda water. Slightly basic, yeah. Rolates. Rolates dissolved in water will deprotonate that. And you get the anion, okay? This is a very unusual amidate anion because it's stabilized by resonance into the two carbonyls. And this is where this low pK comes from. So it's not a very basic amide. And so it's not subject to the limitations of normal amidate anion nucleophiles that are so basic that you have to worry about E2. This guy is not very basic, as reflected in the pKa of the corresponding conjugate acid. And so, but it still functions as a nucleophile, okay? Because it's a negatively charged species, it's a nitrogen, good nucleophile. So you can do an SN2 reaction, in this case, I picked the example from literature, bromopropine, and you alkylate the nitrogen. Okay? And so at this stage, half the job is done, you've established the carbon-nitrogen bond, and all that's left is to liberate the primary amine by hydrolysis. And this will hydrolyze just like any normal amide with aqueous acid at 100 degrees. Or in this case, slightly elevated temperature, to make initially, of course, the ammonium salt because this is acid, and then you work it up with base to liberate the free amine. Typically, all you have to write is the hydrolysis H plus H2O, and it's understood that in the end, the amine is liberated as the free amine by neutralizing the solution. Okay? And that works pretty well, 73% of the hydrolysis step. And the carboxylic acid is then isolated and recycled in this step. So this ensures, because you're blocking two sides on the nitrogen and making it still a good nucleophile by this anion, it ensures that you don't get over-alkylation and that you make the singly alkylated ammonia, namely a primary amine. So that's a good way around things. And so this is named after this character here, Gabriel synthesis. Sigmund Gabriel lived at the turn of the 19th to 20th century. And here's another one that's actually even more powerful and used quite a bit because you can use it to make primary, secondary, and tertiary amines. And it's a trick that nature uses extensively. And it has to do with the fact that carbonyl compounds in the presence of primary amines, or amines in general, will form imines or aminomines. So that's the classic carbonyl plus amine condensation reaction. And remember, this was an equilibrium reaction, and we typically could drive it to the right by excess of one material here, or we didn't emphasize this specifically, but you can also do this by removing water with some material that is hygroscopic. One such thing is molecular sieves, as they're called. It's some aluminum mineral type material that is very hygroscopic. It picks up water and encapsulates it and removes it from the equilibrium. So that was the situation. If you just mix one equivalent each of these two guys, you set up an equilibrium. And the brilliance of this what's so-called reductive amination scheme is that you can trap the imine side of the equilibrium by reduction. And you have to carefully tinker the conditions that to make sure that you only trap the imine, you don't trap the carbonyl. And you make use here of the fact that the CN, with one method, of the CN bond is weaker than the CO double bond. And in another case, you make use of the fact that this nitrogen is basic, and if you adjust the pKa in this equilibrium such that this exists as the protonated species, or is protonated a lot of the time, the protonated iminium charge is more reactive than the carbonyl function in the second method. So what am I referring to? There are two ways of affecting this reduction step. One is catalytic hydrogenation, and the other one is using essentially glorified sodium borohydride. So in the first case, and remember, or I should emphasize this, this is done all in one pot. You don't isolate anything. So you mix this plus that and add the reducing agent, and out comes the amine. Okay? So in catalytic hydrogenation, you make use of the fact that the CN double bond is more easily hydrogenated than the CO double bond, because one reason is because it's weaker. So in this equilibrium, as you add H2 and a catalyst, it will grab this part of the equilibrium, the imine part of the equilibrium, and hydrogenate it in this step here, driving the whole equilibrium, of course, forward. That's Le Chatelier's principle over again. If you use sodium borohydride, and in fact, initially people just dumped in sodium borohydride, they found that if you don't adjust the pH, so just let this thing, just mix these two and let these things roll, then the sodium borohydride would selectively reduce the carbonyl. And that makes sense because there's more delta plus on that carbon than there is on that carbon, because this is more electronegative. So hydride delivers H minus, Coulomb's law, to this carbon, which is more blue than that carbon selectively. But people realize that if you lower the pH of this mixture to about pH 2 to 3, so slightly below 7, okay, then the imine gets protonated under these conditions. And now we have a charged CN double bond, where this blue carbon is now more blue than this blue carbon here, and the sodium borohydride therefore should selectively reduce this guy. The trouble is, and that was the sort of catch-22, sodium borohydride, while stable in protic solvents, and it's used in ethanol, so the H minus equivalent of sodium borohydride doesn't react readily with H plus to make hydrogen gas, whereas lithium aluminum hydride would do this explosively. And the pH that's required to protonate this guy, but make the iminium, there is enough H plus around that now sodium borohydride is no longer stable, and it just bubbles out hydrogen gas and gets destroyed. Okay? So people had to modify the sodium borohydride, and what they did is they replaced one hydride with cyanide. And here's a sort of glorified picture of this reagent. It's called sodium cyanoborohydride. This guy reduces the hydride character of the remaining three hydrides, because this cyanide is electron withdrawing and stabilizes the negative charge inductively on that boron. And that makes these three hydrogens slightly less hydridic, slightly less prone to react with H plus to make hydrogen. And that guy is stable at pH 2, but still transfers hydride to the protonated imine. So after all of this, let me give you some examples. Here's actually industrial synthesis of amphetamine, which is made in large scale because of medicinal applications of amphetamine, as we mentioned last week. And so you start with this phenylpropanone, and if you use ammonia, topologically, if you use ammonia in the reductive amination, the result is a primary amine, because you set up an equilibrium with the imine, and here, in the industrial setting, they use catalytic hydrogenation, which has great advantages because of the ease of reaction, no side products, no solvents, and so forth, or not much solvent. And so these are the conditions they use, 100 atmosphere of hydrogen, nickel, but you could do this under ambient conditions. And you get very fast quantitative conversion, reduction of the imine bond. So this is not protonated, this is just a neutral imine bond that is hydrogenated. Okay? Using sodium cyanoborohydride, example 2, we're now using a primary amine because it gets essentially alkylated by this piece here. It's one way to think about it. You're making a carbon-nitrogen bond initially to the imine, but then you reduce it. So in essence, you're alkylating methylamine or methaneamine with cyclohexyl. This forms a secondary amine. And so you take cyclohexanone, mix it, you get set up this equilibrium, you dump in sodium cyanoborohydride, pH 2 to 3. Under these conditions, that pH, you get protonated iminium. That is more reactive than carbonyl. The hydride reduces this guy. You get a secondary amine. If you do this with a secondary amine, the product will be a tertiary amine, because again, you're alkylating with this piece here. So here now I have a steroid frame, and this is all just finished. The action part is the carbonyl. You mix up the carbonyl with dimethyl or N-methylmethanamine. Common name would be dimethylamine, and it gives you the iminium ion directly. And hydride attacks at the imine carbon, and you get the corresponding product. So now you have a tertiary amine. Okay, so in this mode of thinking of this, not only as nitrogen attacking the carbon, and so you get an amination of the carbon, you can think of it also as an alkylation of the nitrogen. The two are just two complementary views of looking at the same reaction. And if you think of this as an alkylation of the nitrogen, then if you use formaldehyde, then you can see that this actually amounts to a methylation of the nitrogen, because this is a one-carbon unit. So if you take formaldehyde and this particular amine here, you set up the equilibrium with the iminium ion, sodium cyanoborohydride traps it, and you get the methyl derivative. So there's a movie of that to remind you of what actually goes on in detail. So there's the carbonyl. The amine approaches. It goes by addition of the amine initially, kicks out the electron pair. You protonate here to make the OH, and you deprotonate here. That's the first step of imine formation, right? That's the hemiaminal, the addition product of amine to the carbonyl. And then you eliminate water by protonation. Water leaves, electron pair kicks in. This is the iminium species. Sodium cyanoborohydride does the reduction and finishes the job. And finally, those are all reactions. Just to finish off this section, we know how to reduce amides to the corresponding amines, lithium aluminum hydride. So that's another way of making amines from the corresponding amides. Remember that amides are made from acyl halides, best from acyl halides and ammonia, much better than using a carboxylic acid and an amine. So that's the way to make amides. Also remember, which is not on the slide, that amides, as long as they bear at least one hydrogen here, can be alkylated at the amide stage through the amidate anions. And then therefore you can introduce another substituent here and then reduce to the corresponding amine. And finally, the last one, we just did this last week, is the Hofmann rearrangement. That turns the primary amide into a primary amine. And the only difference here now, the difference between this and reducing a nitrile, is that you're losing a carbon. So that if you have a chain of 7 carbons with a carboxamide at the end, that process, bromine and sodium hydroxide, makes the 6 carbon amines. that's all there is to the synthesis. A lot of reviews, so try to organize that. That'll be it for today. There's no lecture on Thursday, and good luck on the exam.